Good afternoon, everyone. I'm Jong-Jin Kim from KIMM. Let me go straight to my presentation. Once again, thank you so much for having me at this wonderful conference. And today I'm going to share with you the results of the research we are doing in our organization. Today I'm going to talk about the automatic technology development. You may be familiar with it. This is the content of my presentation. So I'm going to give you a brief overview of the research done at KIMM. As you may well know, the shipping industry broadly can be defined to have smart marine networks, smart ships, and smart ports. So the shipping industries are consisting of these three parts. Today I'm going to focus on ports. So I'm going to give you a little bit more detail of smart ports. So let's laterally define smart ports. As you can see on the slide, there is this relationship between port and port, and there is something called a ship to port and within the port. Today my focus will be on ship to port as I highlighted on my slide. Today we are using wires for mooring, and the KIMM and KR are co-developing automatic mooring system now. Today, that's the topic of my presentation today. So let me give you more detail on the next slide. On the left-hand side, you can see ship to port, and on the right-hand side, you can also see ship to port, specifically smart port, and autonomous shipping, to be exact. So I'm going to focus on the right hand side. You must be familiar with the cargo tax commercial products, which is automatic mooring system. So I'm going to give you more detail as I progress over my presentation. On the left-hand side, you can see a demonstration ship called Hanbada, which is used by the Korea Maritime and Ocean University. And there are 4 steps, as you can see on the top half of the page. A mooring system normally takes about 30 minutes to 1 hour. This is the general overview of the process. The spring wire is used for the mooring, and my organization is trying to automate this process. If you think about automatic system, normally you think the manual jobs are done automatically, including the wiring system, which is more closely related to autonomous shipping. Taking into account the reality, we believe vacuum system is the most effective way because all ship owners, let's say the magnetic system, for magnetic system, you have to consider the magnetic properties. So some ship owners are not willing to take this system. But unlike the magnetic system, vacuum system can be controlled by static properties, so it has less harmful for ships. That is why it is more welcomed by ship owners. So the KIMM and the KR are working on jointly a vacuum system for an automatic mooring system, and patents of carbon tech will be expired by 2025. So there is no intellectual property related issues using this vacuum system, and that was background for my presentation. Now let me go into research implementation framework, system design, development of prototypes and demonstrations. For all of that, our project just started back in 2021, and we are targeting 2025 for our demonstration project. As I said earlier, this is the demonstration ship called Hanbada. We are monitoring behaviors of this demonstration ship to verify the effects of our automatic mooring system. Let me give you more details on later slides. Our research team consists of 8 to 9 groups or organizations. Kunsan University, KSNU, it considers environmental factors and it works with Caribbean PA. It works on mooring force calculation, and Yongdam University is developing module, and PNU, Busan National University, and BAP are overseeing the left-hand side, and we are using Hanbada, the demonstration ship, and the KIMM is responsible for the design for demonstration, and MMU, Mokpo Maritime University, is responsible for docking assistance system and developing algorithm, and BAP and KMOU are also working on automatic mooring system operation scenarios. And all these systems will be applied to and tested on Hanbada, the demonstration ship. I think this is the part you will be most interested in. We started with Model 1. Now we have a progress to version 3-1. Our focus is safety, mooring capability, and use of space and cost. So they are the 4 key factors, and our system has evolved, as you can see on the slide. But there is only so much we can do in terms of cost, so we are trying to develop our system within our own budget. The hydraulic part and vacuum part, there are these 2 big parts. The hydraulic part, its technical barrier is quite low. It doesn't require any patent. But the a vacuum pad, it has our own. It is using our own patent. So we are a small organization. This is a small part, but we are focusing on this part because that is the most realistically achieved. For a vacuum pad, we have 8 to 10 patents or intellectual property rights for this. As you can see here, the spring is a 2-layer. Its structure is 2 layers. We are also using a spring with a higher rigidity inside because this is quite a rigid structure. We already have intellectual property for this 2 years ago. We are limiting the motions ±6 from left to right. ±6 degree. The margin is ±6 degree. Kunsan University and BAP, they are working with us as well. But to commercialize our product, we have to make prototypes and models, but that has some limitations. We have some limitations to do that. So we are working with BAP for structure, and we are also interpreting fatigue of this model so that we can predict the behavior of the system. This is also our focus, the observation pad. For automatic mooring system, we want to have this we want to achieve this certain threshold. When we started this project, we weren't able to develop 20-ton observation pad. So we first started at the lab. We used the lab system and we tested the sway direction and stir direction. So at the lab scale, we developed a 3-ton of observation pad, and performance was already verified at the lab level. So 8 or 9 organizations are working on automatic mooring system with us. So let me briefly tell you what each of these organizations is doing. Kunsan National University is evaluating static mooring capability, and this year it is focusing on these wall, whether the boarding has an impact on mooring capability. It is also taking a hydraulic test, and when ships are moored, when another ship is moored 30 to 50 meters away, what would happen? And that is also being tested. And the interference effect, it is at an ignorable level because it has only marginal impact according to our test results. And Yongnam University is doing the following. When a ship is moored, according to our system, our system will tell the ship the weather condition, including the waves. And for that, we are using Adam's tool. We are also using mechanical motions, as you can see on the slide. And for this, we are doing this to see the behaviors of moored ships. If you look at conventional system, the passive control was the key, but our system is evaluating a mooring capability in real time to provide a better prediction. Why do we need active control? Passive control would cause a skid mark, making a damage to a moored ship. So we are using active control to minimize damage to a ship, and that can be ensured by our system. This is what I briefly mentioned at the beginning of my presentation. Mokpo National Maritime University is working on this part. They are using 3D LiDAR sensor to predict the outside wall and to predict where observation pad will be needed. So they are using this 3D LiDAR sensor, and for now it is at the lab scale. And by 2025, this system will be on our automatic mooring system. As I mentioned earlier, we are developing observation pad. The end of the observation pad, the rubber part, is most prone to damage. The expected life cycle of this material is only 3 years. We want to lengthen it, so we are doing these tests. And environmental factors should be considered as well, the weather conditions or the sea condition, because they can make some corrosion on the rubber. So we are trying to make these synthetic materials, including rubber and other materials, and we are testing to expect and predict the life expectancy of this new material. We are expecting 2 to 3 years. And we are testing 7 to 8 types of materials. In neoprene and natural rubber, they can be combined to lengthen the life cycle. And first, we are doing interpretation to see if this material can meet our expectations. I've just explained our work at the lab scale, and this is the pad. It is 2 meter length, and it is 6 meter tall. It looks small in the picture, but now it is 3 meter long, and it can provide a more precise mooring capability in the source direction, in the sway direction as well. And this will be commercialized next year according to our plan. The most asked question is that why we affix the obstruction pad. The KIMM and KR, our ultimate goal is not just research. Our ultimate goal is the commercialization of this automatic mooring system. So we have to consider the economic feasibility of the obstruction pad. And if we need more than one obstruction pad, we will have to add one more. So we are always considering economic feasibility. So let me skip some of the slides. As I mentioned, there are many technical information that I want to share with you. Yes, we have some systems, conventional systems developed by Carbon Tech, but once again, we are pursuing active control. Active control requires the calculation of direction between different ships that are trying to be moored at the same time. So for that, we are developing an algorithm. There are many technical barriers and constraints for now, but we are developing this algorithm. And by next April next year, we are trying to verify this algorithm on a real ship. The KIMM is an organization for engineers. So we are not an expert for environmental factors. So that is why we are getting advice from the Korea Maritime and Ocean University. So we have this profile or a pool of data set that offers us 150 to up to 170 different scenarios. These scenarios will tell us different conditions and environment, and they will be incorporated into our system to provide a better prediction. And this is one example of the scenarios, and the scenario is very realistic. And these scenarios are incorporated into our algorithm. This is the demonstration ship. It's about 100 meters long. So once every week, we are testing our system on this demonstration ship. This is the last slide of my presentation. I mentioned in the middle of my presentation, our ultimate goal is not just research. That's not the end of this endeavor. Our ultimate goal is the commercialization of this automatic system. We hope to contribute to national development or national economic development with this new system.
I am from KR. My name is Taechul Park. I'm a principal researcher. Today, my presentation is titled Artificial Intelligence-Based Fault Diagnosis and Prediction Technology for Machinery Systems. This is the content of my presentation. First, I will explain about mass technology development project in Korea, which is led by the Korean government, and I will briefly explain about CBM technology that is being developed at KR. Lastly, I would like to explain about possible digital services based on the CBM technology. As you might all know, from the 1960s till now, ships have evolved, centered around the efforts to enhance the stability and safety of cargo and other technologies. Economic value and operational efficiency have become the important factors in ship evolution. And now we are discussing the development of two types of ships, autonomous ship and unmanned ship. One is a semi-automated ship, the other is fully automated ship. And these are one of the main issues in the shipbuilding and maritime industry. And these technologies can solve many problems, including the environmental issues. So a lot of researches have been conducted. And these are technological classification consisting of mass. It consists of operation, navigation part, and information processing systems. It also consists of data analysis and data acquisition system to ensure safety of the vessel. In order to enable automated navigation of the vessel, we have to collect various data sets and we have to make accurate prediction and diagnosis of the status of the vessels. These will be the basis for the maritime autonomous surface ship development. And along with our efforts for developing mass, we have to establish the logistics and infrastructure system for ports because we have to enable efficient communication between ships and the port. Mass should be operated properly and should exert all the functionalities. And this requires smart port. So in Korea, smart port, smart communication, and smart communication are being developed. And it also includes technologies that deals with smart logistics and optimization of safety and efficiency. There are various element technologies included here, 3D around view technologies, and as Dr. Kim said, it includes automated mooring system, risk detection, and operation control system as well. MAS and smart port need to be connected to each other, and for this purpose, technologies are being developed. When such technologies are fully developed, then we will be able to ensure efficient operation and safety of autonomous ships based on PSC inspection support and berthing and mooring support, as well as loading and unloading support systems. Once we develop all these technologies, then we will also have to work on digital twin technology development. KR has been building small electric fuel-based vehicles, and we are studying on the digital twin technology. We're trying to represent all the objects and physical elements we see in mass into the digital arena. Also, we have to do the technology development in accordance with the regulations of the IMO. And smart port technologies also require standardization. KR is also working on such technology standardization activities. Next is our current status of developing AI-based CBM technology. This is the overview of the project. The Korean government is sponsoring this project. We are developing mass autonomous ship-related technologies. One of them is CBM technology. We have to first of all understand CBM. CBM is to collect real-time data and analyze the data to diagnose any problems with the system and make prediction about the possible fault that could occur in the engine system of the vessel. And we have to use early detection technologies to optimize the maintenance activities. This is the framework of the CBM technology. First, we have to collect and store data, and we have to pre-process the data and come up with the results that will help us in our diagnostics and prognostics activities. Once we verify the results, we can set a plan for maintenance. For development of CBM, we selected some equipment, which includes main engine and generator engine, and pump and purifiers, as well as piping system. These 5 categories of equipment are the basic elements based on which we're developing CBM technologies. And remote maintenance technology is also being developed, but today I am going to skip that part due to time constraints. Anyhow, the CBM and fuel safety technologies have to be developed along with each other, because once a code on CBM technologies is enacted, then we have to work on we have to ensure safety of the vessels. And the 2 technologies are closely related to each other. This is the consortium of the technology development project. When we first developed CBM technologies, we installed the monitoring system on the vessel. It should generate data, and once we collect and store data, we thought that we could get a valuable insight from the data. But if we don't have the fault mode data, it's difficult to develop the algorithm. So in the main ship, we established a land-based test bed, and we arbitrarily caused an error and used that fault mode data. This is the process we went through. For this kind of testing, we have to analyze what kind of error we're going to create, and we have to set criteria over the specific type of fault, and then we have to create the fault mode scenario. We have to develop the test methodologies. These are what we did before. After producing the relevant data, we have to apply this to our algorithm. So we had to analyze the reliability of the data. This slide shows the actual fault mode data, and under the fault scenario, we operated the systems and we reassembled the equipment as well. So the test went on for about 5 hours. As mentioned before, not just engine and generator, but also pump and purifiers went through the testings, and we established a test bed. And under the same research framework, we developed the scenario, we generated the test data, and conducted simulation as well. And Mukpo Maritime, Ocean and Maritime University worked with us. We represented the damage on the vessel through the scenario and analyzed the relevant data. After data analysis is completed, we can have the data framework where we can use the data diagnosis algorithm. We extracted the data feature, as you see here. The data generated through the research process, including vibration data, internal pressure data, and temperature, and many other operational data were collected and analyzed. And our server would be overloaded with such a huge amount of data if we have to apply all the data. So we extracted important features of the data and analyze the data and apply them to algorithm. We collected the time series data and converted the data to recurrence plots and developed the algorithm. Regarding internal combustion engine, we used our source data, and the algorithm performance showed about 95% accuracy. In the case of the pump and auxiliary systems, we also developed a diagnosis algorithm based on machine learning. Its performance level is over 95%. The same goes true for pipes. Various imaging, temperature information, and electrical resistance information and corrosion-related information were collected and measured and analyzed. And based on such data information, we developed the diagnosis algorithm, and performance of the algorithm is also around 95%. For this one, we finished the testing, and next year, in February next year, the demonstration vessels will be delivered, and we need to ensure the performance of the system on the real vessel. At first, at lab level, we use the algorithm and based on the data, error data that we arbitrarily generated, but from next year, we're going to use Polaris vessels and Hannara vessel as a way of demonstrating the CBM system algorithm that we developed. This is the software architecture, which shows what kind of systems will be composed. We collect VMS or AMS data, process the data, and send the data to the server and let it be analyzed, and then use the data analysis for decision-making process. So CBM system should work perfectly even when connectivity is not offered. We have to be able to send the CBM system data to the landside systems as well. This is based on the DevOps concept. This is the current status of dashboard development. This dashboard is installed in the main demonstration vessel. This is the slide that shows various sensors and systems installed on the vessel named Hannara. And we installed various sensors. Although we have to discuss the efficacy or effectiveness of this idea, as you see, this is the system installed in the test vessel from Korea Ocean and Maritime University. We are optimizing the test systems by reflecting the feedback from operators, and we are continuously improving the diagnosis algorithm. Our KISC center receives the data, and we are establishing an infrastructure to optimize CBM system. We are going to enhance the survey or inspection service we provide to the stakeholders. Our future plan. We will continuously receive feedbacks regarding what we developed, and we will make continuous improvement. In February next year, the demonstration vessel will be delivered, and we are going to reflect the feedbacks we received from the relevant stakeholders in the demonstration vessel. And one of the mainstream activities of KR is inspection. Considering this, I would like to explain about possible digital services. Remote inspection or extension of inspection cycle will become possible. So we are trying to establish the technical infrastructure as well. We have to refer to the IMO or IAX regulation. In terms of technology, we are conducting AI convergence research activities to develop digital service inspection method. These are the purposes of our digital service. We would like to enable long-term partnerships, and we would like to make it possible to provide remote diagnosis services through our technology. For consulting services, we need the efforts from all interested parties in the industry, including the register, Korean register, and many other participants of this industry. Regarding the remote and automated inspection technology, we need the joint efforts of all interested parties. As you see here, manufacturers and machine learning domains, as well as class societies, need to maintain their organic relationship with each other. And they need to be able to help each other and have accurate understanding about the status of the business. Although they could have separate business models, but they need to have consistent voice regarding the technologies. And we're trying to digitalize the inspection service we provide. So we are studying very hard to come up with ideas for digital services based on the CBM diagnosis system.
Thank you very much. Good afternoon. So let's just wait for the presentation. There we go. Okay. So thanks a lot for joining today for this session. We're going to switch topic and now started to talk about LNG bunkering and the challenges that we foresee for this developing sector today as well as for tomorrow. So we're going to follow today's agenda as is. So we'll skim through a quick introduction, then we're going to focus on the chance to maximize the compatibility with LNG bunkering vessels, and then we'll switch to the same topic but for the counterpart, basically, so LNG powered ships. First of all, let's start with a quick introduction, who we are. So Trelleborg Gas Transfer is a division of Trelleborg Group, recently founded, recently put together because of some acquisitions of different companies that have been able to play a leading role into this sector from 2006, namely Clo, LNG and Gutteling, to UK, respectively UK and Dutch company that have been able to develop their technology for the flexible transfer of LNG in open seas, starting from 2006, when the first commercial transfer of LNG between ships has been put together using flexible hose systems. Starting from that moment, we have been able to further develop our presence on the market, and then today we count on a quite wide experience in basically any sort of application where a flexible transfer system could be deployed for LNG transfer. Let's dig a bit in the market background. So let's start with a couple of quotes that we like to share. You see the sources back down on the left side. So momentum builds for LNG fuel vessels with more than 500 orders. LNG bunker delivery vessel orders are not keeping up with fuel vessels. These are two very interesting statements that we've been able to find through, obviously, on the news. And they are quite in line with the numbers that so far have been able to put together by third parties like SGMF, as you can see over here, or as well as DNV. So SGMF, in their latest numbers, are counting for a sum of 2 days in operation LNG fuel ships and the ships in order of 913 ships, and they account for 53 LNG bunkering ships. Again, summing what's 2 days in operation and what will come next. I've added another source from DNV, bottom left, where the 913 number is elevated to 970. We're not here to question the numbers, but we need to take in mind the magnitude of such numbers. There's basically 1,000 ships which are going to be in waters start between today and 2028, and they will all have a dual fuel technology for LNG fueling as well. The ratio that we have identified obviously in the next future with bunker ships tends to be quite high. 17:1 will most likely reach 18:1. So we can definitely identify a set of challenges for the bunkering sector. Specifically, two main challenges. First of all, bunker ships are expected to act in the most versatile fashion possible in the coming years, but also today. So we do have a short-term challenge, which is basically the maximization of the compatibility with existing LNG fuel ships, but also have a long-term challenge, which is basically the chance to ensure the compatibility across the operational life of bunkering vessels. The additional challenge is the application of bunkering station standards for LNG fuel vessels, which today are not really there, especially with respect to the position of bunkering hatches, with respect to vessels' hull, provided a population of LNG fuel ships which is growing at a very fast pace and which is progressively more and more diversified, as it's now counting on different types of ships, from cruise ships to container ships to PCTCs, tankers, dry bulkers, and all having different characteristics according to the needs of a shipping industry which obviously keeps evolving. So when we talk about compatibility for LNG bunker ships, we need to deal with different aspects which are all today mastered by LNG bunker ships and their operators. So definitely it's an interesting challenge. It's a nice mix of variables that they have to take into consideration for planning their bunkering operations, but there are two main variables, namely the hose length and the crane reach, which we feel are going to have a specific role for the next future. Because basically these are the two variables which do have quite relevant strategic implications when bunker ships are getting designed and when certain decisions are being taken in order to equip bunker ships with several manifold positions in order to grant a certain working envelope for the bunker vessels. These decisions do have a wide range of implications, CapEx implications, implications at construction phase, but also then implications at operational level. So how can we help targeting such compatibility challenges? We thought of a first solution for bunker ships. Basically, we worked quite hard over these years in order to develop a hose transfer crane solution, able to integrate an LNG hose transfer system and lifting capabilities, ensuring a safe and reliable operation. How we did that? Through a unique cooperation within the industry that put together champions in their technology, hose manufacturer, LNG hose transfer system manufacturer, and a custom-built machinery and crane manufacturer. We used and worked on proven technology, so through a loading system that is already operational in several contexts and ships, and obviously we're also looking at the future. We also grant a full compatibility and suitability with alternative fuels that are expected to jump into the picture quite shortly. These are the actors involved into this exercise. So obviously, Trelleborg gas transfer through Chloe LNG and Gutteling, the two names that you saw before, and the Dutch manufacturer of custom-made machinery, Delmeco. What's the result? The result is the LNG hose transfer crane, a solution that we have started now to build for several clients that can basically target the needs of bunkering operators through a ship-to-ship transfer system based on the maximum capability of any bunker ship, so 2,500 cubic meters per hour, based on 3 flexible lines, but can also cover the needs of shore-based operators in case they want to consider this system to enhance the flexibility of their terminal by equipping it with larger hoses, up to 10-inch, 3 flexible lines, granting a maximum flow rate, which is a bit higher than what we saw before. We achieved these also with thanking to an existing technology, which is basically our emergency release coupling technology. So we count on a flexible ERC positioning because basically we can play with the layout of the transfer system either by positioning the ERC in the conventional position, which is basically right before the flexible line, or like in this example, we can also position the emergency release coupling in a suspended fashion in order to match also the needs and expectations of all the clients involved in bunkering operations. The crane is made of different components. You can see them over here, so starting left to right, pedestal, the different arms and sections, part of it, the sliding beam, which is a critical part for the to grant the operational envelope of the crane, and then the integrated hose transfer system based on the same technology that is already available on the market from many years. We have summarized a set of pros related to this solution, a set of advantages, starting from obviously some mechanical advantages, removal of swivel joints, some operational advantages related to purging, related to the manipulation of the hose in order to achieve different configuration scenarios, and so on. What is critical in terms of advantages is to stress the chance of working on an enhanced envelope. The main characteristic of bunker ships today and also in the future will be, as we said before, the versatility, the capability to reach different manifolds and to be able to perform operations safely and efficiently with different types of clients. Having an enhanced working envelope is a big advantage at the commercial stage. You can basically increase the number and population of your clients, and by thinking in advance about what is going to be the operational envelope, you can also open up for new business opportunities. Obviously, being able to bunker a cruise ship with a manifold that is a few meters above the water surface, and at the same time bunkering 25,000 container ship, it's a complete different game. And that's the reason why we like to stress the attention on the working envelope, because we feel this is a solution which could cope with the needs of operators that like to challenge themselves with different types of scenarios. Well, with the aid of some pictorials, we put together some slides showing how a crane operates or is expected to operate on a bunker ship. So starting from a parking position and keep going with connection, loading, post-transfer operations starting from draining, specifically also helped by gravity, and then disconnection, and ultimately back to the parking position. Pictorials are always very useful. We like images, but I think a video, it's usually better in such a situation. What we like to see over here, apart from the nice behavior of the whole system, is the concept of manipulation. It's basically having the chance to maneuver different points of the flexible hoses through different range of winches in order to change the position of the whole transfer line, and then basically having always the chance to overcome any possible challenge within the operational envelope. Obviously, this is a solution which works perfectly in certain conditions, and especially when the bunkering configuration starts to be extremely challenging. But it's a solution which sometimes needs to be deployed also together some other features which will take into consideration the position of the receiving ship and specifically their bunkering station. So we need to take into consideration also a set of variables which affect directly the operations for the LNG power ships, namely the bunker station itself, its layout and position, obviously the short time that these companies are able to grant for bunkering operations, and then ultimately we also have to take into consideration, without forgetting, the different rules and regulations which are get applied to such solutions. If we switch to the first family of variables, basically so far we've encountered a wide range of challenges. As bunker stations tend to differ all each other, as I was saying before, today there's no specific standard on to build a bunker station across the industry. There are for sure guidelines to build the manifolds, but they always have to take into consideration the whole picture. And the whole picture is made of practical aspects. Are we dealing with an open deck? Are we dealing with a closed hatch? Do we have bunker station doors? How do they open? Do they slide? Do they open down? Where is the manifold located? Is the layout matching the prescriptions of SGMF, for example? Or are we dealing with a more compact and squeezed layout? How do we deal with saddles? Do we need fixed saddles? Do we need movable saddles? And so on. Do we have drip trays, water curtain? Do we deal with lifting equipment? So many variables in a very short space. So also in this case, we wanted to challenge ourselves, and we wanted to basically work on a solution which could, if I can get to the next slide, maybe. Sure. Let's see. No, it doesn't want to go to the next slide. Sorry. Try to see if it's what's happening. Okay, easy, good. So we wanted to basically work on a solution, as I was saying, that gathered the needs of receiving ships. And so we've been able to put together a handling solution in this case, which basically helps the control of any hose transfer system inbound from a bunker vessel, helps reducing the cost and complexity of lifting equipment within the bunker station. Is also able to do a bit of lifting, so handling certain weights within the bunker station, and most important thing, can help to put together basically bunkering operations in a safe and effective way with minimum operational input from the crew. Time keeps being of essence, so it's definitely another solution which takes that into consideration, but also something which helps matching and maybe even overcoming the challenges encountered by conventional cranes, davits, or any sort of other equipment which is deployed in bunker stations, which is also often cause of potential risks for operators. that's the solution that you see in our workshop. So we call it bunker station arm. So basically it's a protruding arm which is able to extend out of the LNG fuel ships, can capture the extended hose from the LNG bunkering vessel. And basically it's a mechanism which helps the lowering down of the hose to the manifold, and obviously helping the connection, reducing also the need of all winches, pulleys, or any further aid which is deployed within the bunker station. You can see some images again over here. So when it starts to work in a fully extended position and then in fully retracted position, but also in this case, the video is always helpful to understand well how the system is expected to work. So we have simulated here bunkering station connection, basically. So on the right side, obviously, the bunker vessel, on the left side, receiving vessel. In this specific case, we have deployed movable saddles, but obviously we're gonna play with any sort of configuration with respect to saddles that will be taken into consideration by the bunker station. So it's definitely, well, a solution that in certain conditions could help the basically maximizing the flexibility of bunkering operations. So let's get to some conclusions and takeaways. We see a set of challenges for LNG bunkering today and for the imminent future. And compatibility is one of the main that we have to take into consideration for both bunker ships and receiving ships. For bunker ships, our suggestion, our view is to consider the extent of the working envelope for vessels today and into the future. So do not stop to what you expect to happen today according to present business plans, but also try to challenge the assumptions for the next future, and also keep considering rules and regulation of receiving vessel, because this will definitely have an influence and an impact on operations. On receiving side, let's consider any challenges within the bunker station that could result in compatibility issues with an LNG hose transfer system. There are different variables that we saw before and might be taken into consideration by operators. And let's take the necessary steps also to maximize the flexibility of the bunker station. What we see next in terms of bunkering, this is a sector which will have a lot of challenges, as we saw before, with respect to the numbers of available ships in the next future and the number of available bunker ships in the next future. So what could help next? Other ways to basically deliver LNG, other ways to distribute LNG, but also to bunker LNG. So specifically ship to truck or truck to ship, skid-based solutions, which we feel, together with our help, will be able to keep it running with respect to LNG bunkering in different parts of the world, and obviously according to the different cases and bunkering scenarios that we see are now more and more diversified and will be more and more diversified in the next future. Thanks a lot for your time and attention.
Hello, everybody. Thank you for attention to be here. My name is Stefano Bottino. I am a Global Sales Manager for Full Supply System at Alfa Laval. A short introduction about our company. We are a Swedish company with global presence, also here in Korea, and we have a very large portfolio of marine solutions for boiler, gas treatment, and also marine separation, heat exchange, water treatment, and further decarbonization solution recently joining us, like air lubrication, wind propulsion, and digital solution like StormGeo. And many of our solutions are ready and available for treatment of alternative fuels like LNG, LPG, and biofuel. But today we will focus on latest development about methanol and ammonia.
Hello, I'm David Jong, Business Development Manager at Alfa Laval Aalborg. And we prepared this presentation as the core presenting, but the situation here is a little bit different than we expected. So we are a little bit come and go, but please take our apologies for that. And in this presentation, we'll take a little bit zoom out compared to the previous presentations. So we will talk about the very broad aspects of our development activities. That has been actually cut down because as you see, we have many different activities, different product groups in the company. So we had to take the short introduction of different things.
So starting about methanol, when you look to methanol fuel vessel, you have to take in consideration many aspects related to the fuel itself and its properties, rules and regulation that are growing and growing because it's a new solution also for class registers, and also the ship design and operation. If you look to the properties, the main ones to care of is boiling point, combustion, safety, and others. And instead, this fuel is affecting the ship design for tank design, bunkering, propulsion, electrical power it demands, and so on. Alfa Laval is matching the market demands with some solutions. The fuel supply systems, basically transferring the fuel ready to be burned from the tank to the engine, the Framo pumps, the plate exchangers, boilers, now ready for methanol, and also the tank management by Scanjet. If we look to the fuel supply system, yes, we now leave you to look into a video, short video about methanol for Alfa Laval.
For many ship owners, green methanol is the next step in fuel decarbonisation. Already, the first methanol-fueled vessels are setting sail with Alfa Laval technology on board. It's taken much to get this far, including close work with industry thought leaders and front-running ship owners. Methanol poses tough challenges in fuel supply, fuel changeover, and energy management. For many vessels, it will be one of multiple fuels on board. And its lower energy content puts energy efficiency in even sharper focus. At Alfa Laval, we're combining knowledge, technology, and experience to meet methanol's challenges. As a valuable technology partner, we work with our customers and industry leaders to make shipping more sustainable. The Alfa Laval Test and Training Centre is a hub where energy and environmental technology to meet the net zero goals is taking shape. It's our focus point for methanol innovation and developing sustainable solutions to help our customers decarbonise. Our FCM methanol low flashpoint fuel supply system set sail in 2015, and this long-proven first has expanded into a broad methanol offering. From the first methanol-fired boilers to methanol handling solutions, energy management solutions, and now even connected bunkering support. Many different solutions will be needed in the maritime energy transition, and Alfa Laval's methanol offering is one part of the whole. It's surrounded by a fuel-flexible portfolio of new green technologies and supported by a global service network built on over 100 years of maritime experience. We're here to support you in full, from succeeding with methanol to excelling in a decarbonised future.
If you look in the first solution from a long list, is the full supply system that, as you have been able to see from the video, started in first delivery in 2015. The first generation of our solution. Then we have many developments, and today we are already in the third generation of this system. We have different units already delivered for the first and second generation. The solution is basically a two-stage pump. We're starting with a couple of skids and then switching to one for being more compact and easy to install on board. And of course, starting from the two-stroke main engines, and the pioneer in this marine propulsion has been MAN, and we follow their requirements since the beginning. And today, our third generation is already contracted 55 units, and it is state-of-the-art for this technology, being a compact solution with some Alfa Laval core technology inside, like plate heat exchangers, very well engineered, and so much more compact than in the past, and we have an energy efficiency software inside. And today it is able to feed both main engine, auxiliary engine, and also boilers if needed, and is compatible with the technical requirements for both, from both MAN and WinGD two-stroke engines. The application is already available and contracted for basically the main categories of cargo vessel, tankers, container, bulk carrier, and ro-ro. We can already count 200,000 running hours in operation on board the vessel. And we are now ongoing joint development agreement with both WinGD and MAN four-stroke department. And it is a system that is connectivity enabled and has been part of the journey of Laura Maersk, who has been the first completely methanol fuel vessel, both auxiliary engine and main engine, this year. Next year, we will be present as first retrofit for container vessel. We'll have a global availability in supply chain, being both in Europe and in China, and we will develop a four-stroke optimized solution. And also we'll add the full valve train in the technology available. As you can see, all the vessels in operation with methanol fueled have an Alfa Laval full supply system on board.
So next on the slide are the products that we have had for the longer period, for several decades. So semi-welded plate exchanger has been used on the LPG, ammonia, and the methanol up to 65 bar. And it is one channel is welded and the other channel is gasketed. And it's a robust system that has been used for many applications. And when there is a need for smaller the space for the installation and also the low weight, then we have another solution, that's Alfa Laval Nova and CBM type of the plate exchangers. And we also have been, the Framo is also specialized in supplying the methanol pumps that has been used in the configuration of this pump that is submerged in the methanol storage tank. That has the benefit of using that is we can delete the hazardous pump room, and the shaft is very short, so the reliability is better with this system. I will just skip, but it has, and this technology has been used in the various applications ranging from FPSOs, chemical and the methanol tankers, and as well as newly the methanol fueled container ships that has come into the market recently. And the Scanjet is now part of Alfa Laval companies, and it is specialized in the tank management system with a very good track record. It has its system includes the tank cleaning system, also the cargo monitoring system. But I would like to put more focus on this PV valve that is a dual nozzle system, and it's minimize the ventilation and the pressure fluctuation inside the tank. You see on this graph, on this side is the conventional the fluctuation of the pressure, but using the dual fuel, dual nozzle system PV valve, then this is the tank pressure is much more stable. So it's a good benefit. Next one, I would like to talk about the dual fuel boiler that has been used for the methanol as a fuel. For that, we have the smaller the boilers that use the steam atomizing, the side firing configuration. And it is now applied for the new build, and we are also offering the boiler system for the methanol ready concept. And the retrofit is in principle possible when you have the boiler body that is compatible to this type of burner. And for the larger boilers, we are working on the system design development, and we recently started the testing. And we are, I'm proud to say that for the methanol fueled the boiler, we have secured 100% market share until today, even though the adoption rate has not been so great. That concludes our presentation about the methanol, and now we'll move on to the ammonia fuel ships. So similar concept as previously Stefano introduced. So we consider three aspects. And when we have the ammonia as a fuel, then we have some more consideration about what is the boiling point, which is minus 34, 35 degrees. So the ammonia exists as the gaseous state. So there will be additional considerations. And also the combustibility of ammonia is also very challenging. And the safety aspects is another challenge to overcome. And to put that the properties of ammonia together with the ship design aspects, then we come to think that the fuel supply system, of course, it will still be needed because there will be a main engine or other type of the propulsion that use the combustion of the ammonia, and the pump system will need to be installed to supply the pump to the fuel system, and the steam boiler and is also will be required because there's a heat demand. And we also came to two different additional products that are the ammonia cracker and the vapor removal system, which we'll talk about in the later slides.
Same as methanol fuel being a carbon neutral solution, Alfa Laval strongly believe in ammonia as the first net zero fuel will be available on the market, and same for the methanol fuel supply system. We want to be the first partner for the industry and also the proven technology ship owners, shipyards can address too. For this reason, what we are already doing is to join some development programs with major stakeholders like the Zero Carbon Shipping Maersk McKinney Center, with solid oxide fuel cell for Maritime project that will be tested at the end of this year, and we supplied already the cold works for this utilization, and it will be executed in Alfa Laval Aalborg Test and Training Center. We have the same project ongoing with WinGD two-stroke engine that will start second quarter, end of the second quarter next year. We are supplying injection test rig and single cylinder fuel supply systems for both of them with a land-based vent treatment system. And the Ammonia On project, which is an European funded project that will be for land-based application with many companies contributing, and we supplied the same scope. It will be started Q3 25.
For the ammonia pump system, our approach is to take the benefit of the two different worlds that's using the Framo hydraulic cargo pumps and also the electrical seawater lift pump. And they will form the basis for the electrical gas pump. And this system is now built based on the experience of the 8,000 the pumps that are supplied for the marine and offshore industry. I think the time is a little bit too short, so I will skip quite a bit in this part. But the principle is the same, that it is top penetrated, short shaft driven. And the highlight I would like to mention is the first ammonia pump. We are targeting to have the delivery in 25. And for the combustion that's going to be used for the boiler system, then our approach is that we will do the more in-depth research and the preparation than what we normally do on the boiler development, because the ammonia has a very challenging combustion the behavior. And we have started doing the laboratory tests since the beginning of the year. And that's based on the using, this is the view of our test and training center you have seen from the movie before as well. And this is our backbone of doing all these test activities. And we installed the small laboratory in another the part of the building. And we achieved a successful ammonia combustion with our pilot fuel based on this. And now next step is that we will move on to to find the optimal condition for the ammonia the combustion, and also we do the test at scale to place that into the 2-ton boiler that are already installed in the test and training center. And the ammonia combustion is also linked to the other type of the solutions that are the ammonia cracker and the ammonia vapor removal system, which I will talk in the next slide. So as Stefano mentioned, AMMON project is the project we are working in Alfa Laval together with the other partners as mentioned on the bottom of this slide. And in that, the main purpose of this project is to generate electrical power out of the ammonia as a fuel. And the first step is to to put through the ammonia into a cracker that will break down ammonia into nitrogen and hydrogen, and the hydrogen will basically be used in the solid oxide fuel cell system. And as the system will require some heat to operate this system, we have the burner and the heat recovery system and also the recirculation system to optimize the system efficiency. The objectives are like this. I will not go into much details, but our aim is to make an 8 kilowatts unit that will be reliable, and it has generated 70% system efficiency. So ammonia vapor handling system is the next one on the line as we speak, and in that we have we identified that there will be different scenarios that ammonia in gaseous state will be generated, and that it will need to be handled, this vapor, the content will need to be reduced or removed before it's ventilated to the atmosphere. In that, we also think there will be various scenarios, small flow to large flow, low pressure to high pressure, high ammonia trace to low trace, and so on. And with that, our approach that we look at both combustion and absorber-based solution, and each solution has its own pros and cons. So maybe it's good to start a discussion about having two systems on the drawing board, and think about what is the ups and downs of these systems. That concludes our speech about ammonia, and very quickly, not only for the ammonia and the methanol, we are also working on the various solutions that are fuel independent. One of them is the StormGeo solution. That's the help the optimize the vessel's operation through giving the let's say advice on the go, what is the best road to take, and considering the fuel consumption, the ETA and stuff like that. And in this system we are adding the two additional features that will be give the benefits for the ship owner and also the ship operators to simulate and monitor what is the expected the fees that will come from the EU ETS, and also what is the current status and the expected the rating of a CII if the vessel continues to work in the same manner, and so on. So the conclusion, we are working on many things on the ammonia and the methanol. And for the methanol, we have secured developed quite a few the industry-leading products, including the plate exchanger pump system that has been used for many years, and the methanol fuel supply system as the new system to the market based on the market needs, and also the dual fuel boiler. And for the ammonia, we are starting our journey, and it's being accelerated as the market demand seems to be on the rise. And also we are working on the fuel independent solutions. There are so many activities ongoing. We could not put everything in this slide. So if you need more, if you want to know more about that, please visit us on our stand at 2C29. Thanks very much.